Welcome to our lab on determining the initial velocity of a Nerf bullet using a ballistic pendulum. In this experiment, we aim to calculate the initial velocity of a Nerf bullet shot into a water bottle which acted as a ballistic pendulum. We utilize the principles of conservation of energy and momentum. First, let's discuss the setup and procedure. We created our ballistic pendulum using tubes and string, with the string attached to the bottom half of a water bottle inside the bottle. We placed 5 pennies wrapped in a paper towel which would act as the pendulum's mass. Next, we loaded the Nerf gun with the bullet. When the bullet was fired, it struck the water bottle, resulting in a perfectly inelastic collision. After the collision, we measured the maximum height to which the pendulum swung. This is a crucial part for our calculations. Using our recorded data, we calculated the initial velocity of the pendulum system immediately after the bullet was struck, which was found to be about 0.767 plus or minus 0.14 meters per second. To find the bullet's velocity just before the impact, we applied conservation of momentum. The calculated initial velocity of the bullet was 16.18 plus or minus 2.98 meters per second. This experiment effectively demonstrates how to determine the initial velocity of a projectile using a ballistic pendulum. By measuring the mass of the objects and the change in height of the pendulum, we utilized principles of physics to arrive at our results.
Alright, so I'm going to be talking about the background of our lab. So we're trying to find the initial velocity of a bullet before it hits a pendulum. So here we have the pendulum. We have the bottle here, and we have the bullet here. So this is called the isolated system. And then we have to think about it a different way as well. The perfectly elastic collision. So the perfectly elastic collision is where the kinetic energy from the bullet is released into the pendulum, and the isolated system is where none of the objects are interacting. So for this one, we have the same pendulum, but now we have the bullet attached to it. So they have a combined mass, and they also have a combined velocity. So this is, from here it's gonna go up after the perfectly elastic collision. It's gonna go up and hit a certain height. This is called the H maximum. So we can write H max here. And so now we're gonna use 2 equations to find the initial velocity of this bullet right here. So let's see here. The first equation is 1/2 mv initial squared is equal to mgh max. So these are same. This is this. So this is the maximum height that the pendulum will reach with the force that the bullet is giving to it. So yeah, so this equation is basically used to find the velocity of the pendulum of the bottle or like the whole, both masses combined, the initial velocity that it has. So now we're looking for this, so we have to plug this into the momentum equation, which is m1 v1 plus m2 v2 is equal to m1 plus m2 v initial. So now with our velocity that we found from this one, we have to plug it into this one, and from this one we can calculate our initial velocity for the bullet. And that's just a little bit of background for our lab.
Okay, so This is Penn, and I'm going to be describing how we found our final value for the initial velocity of the bullet. So I took the liberty of writing our initial known measurements here. So we found that the initial height of the pendulum was 0.13 meters or 13 centimeters, and the maximum it reached was 16 centimeters or 0.61 meters. And the mass of the pendulum, which is this, is 19.49 grams, and the mass of the bullet is 0.97 grams. So the delta height, which is the difference between the initial height and the maximum height, is going to be, let me write that here, delta H equals, I'm going to write it just in meters, 0.03 meters. So we're going to use that later. So when we start, we got to think, how are we going to find the initial velocity of this bullet? Well, a good place to start is finding the initial velocity of the pendulum bullet system after they collide in the inelastic collision. So after the masses combine, what is the initial velocity of that combined thing? So to do that, we're going to use the isolated system energy analysis approach. So let's start doing that here. We know that M, we're going to cancel, but this is, just to clarify, this is the mass of both MP and MB. So mgh max equals 1/2 mv, I'm going to do mv prime squared. So we're solving for mv prime squared. So we can cancel the m's, doesn't really matter what they are, but we know that they do represent the combined masses, and then we write 2 times g times h max. Now, if we're going to solve this, we would then show that v prime equals 2 times 9.8 times 0.03, and I already have this calculated. This is 0.767 meters per second. So then we're going to look at, okay, so we know the initial velocity of this when they were combined was 0.767 meters per second. Good. Now, how do we, from that, find what the initial velocity of just the bullet was? Luckily, we have the laws of the conservation of momentum. So the conservation of momentum is going to tell us, make sure you know that this is for an inelastic collision. So for an inelastic collision, the masses combine, they stick together. So that means that we have to write it as m1v1 plus m2v2 equals m1 plus m2. And then what's the velocity here? Is going to be exactly v prime that we solved for here. So now we can realize that initially the pendulum, I'm going to rewrite this as mb, mp. Initially the pendulum, although it had mass, it had no velocity, it was not moving. It's the bullet that gave it that momentum of velocity. So we can cancel that, and then we can divide both sides by mb. Let me clarify that here too, mb, mp. Okay, so now we have it in terms of all our initial conditions and all the values that we solved for. So now we just plug it in. Okay, v1 equals, let's see, 0.97 plus, what do we have, 19.49 over 0.97 times 0.767 meters per second. So luckily, we don't have to convert this to kilograms, because even though it's not in SI units, it's going to cancel. The units are going to cancel. We write grams here, they cancel, because and it's going to be a scalar multiple. So when we solve this, we can plug this into our calculators and find that we get a final answer of 16.18 meters per second, which is what? What is V1? V1 represents the initial velocity of the bullet moving this way. So make sure that we know that our axes are pointed like this is positive X, this is positive Y. And that's going to give us our final answer. Thank you for listening.
Based on the data that was physically collected, the velocity of the Nerf bullet right before its perfectly inelastic collision with the ballistic pendulum was 16.18 plus or minus 2.98 meters per second. Some possible points of error that could explain the standard error in our final velocity are, one, the need of a more accurate tool to measure the height the pendulum swung upwards, air resistance, and also just possible error or unevenness in setting up the strings of the ballistic pendulum. If the experiment was repeated for more accurate results, the use of a measurement laser sensor to measure the height the pendulum swung upwards would be more accurate and less at fault to human error when compared to a slow motion video of the pendulum next to a meter stick. Thank you, and this is our lab.